Assalamualaikum everyone. This episode focuses on a problem that involves thermal stress, specifically finding the force necessary to maintain the original length of a rigid metal rod despite change in its temperature. So join me, stick around, watch and learn. The question is, a cylindrical brass rod is 10.0 centimeters in length and 0.500 centimeters in radius at an initial temperature 25.0 degrees Celsius. How much force do you have to apply to each end of the rod to maintain its length when the temperature is decreased to 13.0 degrees Celsius? Are the required forces tensile or compressive? Brass has Young's elastic modulus of 9.0 times 10 to the 10th power Pascal, and its coefficient of linear expansion alpha equals 2.0 raised to the negative 5 power per Celsius degree or per Kelvin. Identifying the given data, we have the initial length of the brass rod, denoted by L naught, equal to 10.0 centimeters. The radius of the cylindrical rod, denoted by small letter r, equals 0.500 centimeters. The initial temperature of the rod, labeled T naught, is equal to 25.0 degrees Celsius, and its final temperature, capital T, is equal to 13.0 degrees Celsius. We're also given the Young's elastic modulus of the material brass, which is equal to 9.0 raised to the 10th power Pascal. And the coefficient of linear thermal expansion for brass, denoted by alpha, is given as 2.0 raised to the negative 5 power per Celsius degree or per Kelvin. And our target variable is to find the magnitude of the force, capital F, that you have to apply to each end of the rod in order to maintain its original length when the temperature is decreased to 13.0 degrees Celsius, and also to describe if such force F is tensile or compressive. So this will be our solution. We first get the change in temperature delta T, all right, which is the final temperature 13.0 degrees Celsius minus the initial temperature 25.0 degrees Celsius. So we get a negative change in temperature, negative 12.0 Celsius degree or Kelvin. We also find the cross-sectional area of the cylindrical rod, all right? Area, of course, is pi r squared. So substituting the value pi multiplied by the square of the radius, the rod, which in meter is equal to 5.00 times 10 to the negative 3 meter. Doing our math, we will get the cross-sectional area equal to 7.85 times 10 to the negative 5 meters squared. All right? So, we can proceed in finding the force capital F. Okay. Using this working equation, F equals negative capital Y multiplied by the cross-sectional area capital A times a constant alpha referring to the coefficient of linear thermal expansion of the material, all right? And of course, multiplied by the change in temperature delta T, all right? This formula is the result of combining the formula for Young's elastic modulus capital Y, which we know is equal to stress over strain, all right? Stress is just the ratio of the force, either compressive or tensile, over the cross-sectional area, all right? While the corresponding strain, of course, is the amount of change in length, delta L, over the initial length, L naught. So, the other equation refers to the equation describing the what we call thermal stress, all right, whose change in length or the elongation due to thermal expansion or contraction can be expressed as the product of alpha or the coefficient of linear thermal expansion or contraction multiplied by the initial length L naught and the change in temperature delta T. Alright? So when these two equations are combined, the variables delta L as well as L naught are common in both equations. So presumably these variables have been cancelled and we just came up with this working equation for calculating the force capital F. All right. So as we can see in this working formula for capital F, all right, the force F can be expressed as the product of Young's elastic modulus multiplied by the cross-sectional area of the rod times the coefficient of linear thermal expansion alpha and times the change in temperature capital T. Notice that there is a negative sign. Why is this so? The negative sign simply implies that the force capital F, okay, that is exerted on the material, which is the rod, all right, is in fact opposite in direction but equal in magnitude, all right, to the force that tends to, in this case, okay, the force that tends to decrease the length of the rod because there is a decrease in its temperature, all right? So without the force, capital F, the tendency for the rod is to contract, all right? So when it contracts, the original length will be shortened, all right? In order to prevent such contraction or decrease in the length, L naught, there is a need for the application of this force F. All right. The force capital F must be equal in magnitude but opposite in direction. All right. To the force associated to the thermal contraction of the material. All right. So, substituting the given values for all these quantities, we now have negative 9.0 raised to the 10th power Pascal multiplied by the value of the computed cross-sectional area 7.85 raised to the negative 5 meters squared times the value of alpha 2.0 times 10 to the negative 5 per Celsius degree or per Kelvin. And of course, the change in temperature negative 12.0 Kelvin. And doing our math, we will get the magnitude of the force capital F equal to 1.7 times 10 to the third power Newton in two significant figures. All right. We are emphasizing also that the force F here has a positive sign. And as you notice in our computation, the formula has a negative sign and the change in temperature is negative, resulting to a positive sign for our computed force F. All right? And as mentioned earlier, the force F here, must be exerted at each end of the rod, all right, in the outward direction. So it is as if the force tends to stretch, all right, the rod, all right. Hence, we describe this force to be a tensile force, all right. It is a tensile force, which simply means opposite in direction to the compression or compressive force, all right. As a result of the change in or decrease in temperature, all right, without this force, the rod would tend to uh, shorten its length. So to prevent that, such force, capital F, has to be applied. All right? And in other words, this force will balance the compressive force, and as such, it must be a tensile force. For our evaluation, we say that the stress on the rod in the force on it is indeed relatively large. Such thermal stresses must be accounted for, especially in the field of engineering. Engineers must account for thermal stresses when designing structures, such as the use of expansion joints on bridges or bridge decks, since the concrete bridge decks can change length due to thermal expansion. Finally, we reiterate the key concept applied in this problem. To keep the length of an object constant when the temperature changes, forces must be applied to both of its ends. The required stress, or the force per unit area, is proportional to the temperature change. So that's about all. Till the next episode, inshallah. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.